Hello, welcome to our first video on our rotation unit. Okay, now we've done a circular motion unit. This is different. We're going to be talking about angular or rotational motion, and we're going to start off with angular kinematics or rotational kinematics because it's a nice parallel to what you did in the beginning of the year. Matter of fact, the entire rotation unit is going to be a very nice review of some topics that you did in the beginning of the year, but looked at through a different lens and in slightly different cases than you've looked at before. So far this year, we've been dealing only with linear motion, or technically the actual word for it is rectilinear motion. Okay, so rectilinear motion is defined like this. Rectilinear motion is motion in which an object moves along a straight or even a curved line, or path, I should say. Either straight or curved path. Now, you might say linear, that implies straight. It doesn't. Rectilinear means straight or curved path. So we've done, like projectile motion, think of, for instance. We've done examples where objects start up at some height and then go down to the ground. Okay, that's rectilinear motion, an object moving along a straight or curved path. We're going to start talking about angular motion, or rotational motion. And this is motion in which an object turns about an axis. Okay, so that would be something, and it is going to look a little bit like circular motion right now, but we are not, in circular motion we were somewhat concerned with like the speed, the linear speed, how much distance was traveled in a certain amount of time. We're not really concerned with that here. In linear motion we measure distance in meters, but in angular motion we measure angles of rotation. Okay, so while linear motion we might be concerned with how far has the object traveled from, let's say, here to here. In angular motion we want to know what that angle is, and you're not going to like this. Sometimes we do measure in degrees, but most of this unit is going to be in radians. We measure angles of rotation in radians. Now I know that a lot of people don't like radians, they don't quite get them. Let's do a very quick refresher. Here's a circle. Alright, pretty decent looking circle. And usually when you get a circle, there's a picture, or there's a little sketch of the circle's radius, and that is r. Okay, that's displayed right there for you. Now, what a radian is, it's a way to measure an angle. A radian is found by taking the radius of a circle, and then I'm going to put this in quotes, you just kind of lay it on the circumference. The circumference is the perimeter of the circle. Okay, so take the radius is this right here, this long, and just kind of imagine if you could like pick this up and you could drape it along the circumference. Okay, a really good way to do this is to take like a piece of string and then align the string along the outside of the circle. It'll go to about here. And the neat thing is, no matter how big your circle, it will go to about there. The ancient Greeks discovered that for any circle, it takes slightly over 6 radii of length r to complete the circumference. Except they didn't say slightly over 6. They said 2 times this number that's slightly over 3. This is where pi comes from, okay? What I imagine happened is the ancient Greeks realized that for a half circle, it took about a little bit over 3 radii draped around the circumference to make one half circle. And they just came up with this number and they said, this is going to be pi. Okay, we're going to set this, it's always equal to this number. So if half a circle is pi radii, then a full circle would be 2 pi radii. And then instead of calling them instead of referring to the amount of the size of the radius as we drape it around the circle, we started calling it a radian because we're measuring an angle with that. So this kind of makes sense because to complete a circumference, we know circumference is c, it takes 2 pi slightly over 6. Remember, pi is 3.14, so 2 times 3.14 is about 6.28. It takes 2 pi slightly over 6 times the radius to complete one circumference. Recall that a full circle has 360 degrees in it. In radians, a full circle is 2 pi radians, so we can write 2 pi radians. So, to convert between degrees or radians, and the symbol for radians is usually just rad, and I'll start abbreviating it like that later, you use unit conversion. And the factor, the conversion factor, depending on which way you want to go, either 180 degrees over pi radians, or the inverse, pi radians over 180 degrees. That's used to convert between degrees and radians. In this unit and this unit only, we're going to be dealing with radians almost exclusively. Now, seeing this equation right here brings up an interesting relationship between linear and angular variables. We see c equals 2 pi times r. We know what c is. C is a circumference. It's literally a distance in meters. It's a perimeter for the circle. So c is a distance in meters. R is the radius. And 2 pi, well, think about it. C is a circumference, the perimeter of the entire circle. 2 pi is the number of radians in the entire circle. As a matter of fact, it's the angular displacement, okay? If you were to start here and then rotate all the way around, your angular displacement, the angle that you've traveled through, is, well, 360 degrees, but in radians, that's 2 pi. Look, it's in the equation. This is the angle in radians. The pattern doesn't stop there, though. What if you look at just a half circle? Well, a half circle is obviously half of a full circle, so I'm going to use the variable h. The size of a half circle, or the perimeter of a half circle, not counting this part right here, the size of a half circle would end up being 2 pi r divided by 2. That's just going to be pi times r. Again, h, the half circle length from here to here, is the distance in meters. R is the radius. And pi, well, let's think about it. If this is the distance for a half circle in meters, imagine you're running around the perimeter, you run through a half circle right here. Well, the angular displacement there is pi. 1/2 circle is pi radians. Because a full circle is 2 pi radians, a half circle is pi radians. So again, we have this thing that shows us the angle in radians. And you start to see a pattern emerge. I'm going to do one more. What about a quarter circle? I'm going to symbolize that with Q. A quarter circle, let's see, this would be a distance in meters. Okay, don't get this confused with any other H's or Q's. I'm just making up this variable right now. Well, a quarter circle, it's got to have half as many, it's half as much distance. It's also half as much of an angle. If pi was the angular displacement from here to here along a half circle, the angular displacement around a quarter circle should be pi over 2. And if you remember your trigonometry and what you learned in math class, geometry, pi over 2 is equal to 90 degrees. It makes complete sense. This is the angle in radians. And then once again, r is the radius. Now you should be able to see a pattern emerging here. And the pattern is this. If you want to relate the linear distance to the angular distance, or actually the term we usually use is angular displacement, it seems like you should do this. The linear distance is equal to, and I'm going to switch up the order here, the radius multiplied by the angle that is rotated through. Okay, if for the full circle, we're starting here, rotating all the way around, 2 pi radians. For a half circle, here to here, pi radians. Quarter circle, here to here, pi over 2 radians. Angle rotated through, and we're going to make a note of that in just a second. This is also known as the angular displacement. You've actually seen this equation before. You have variables for this equation. You learned this back in math class. The linear distance for a section around a circle is s. The radius is r, and the angle rotated through, or the angular displacement, is theta. Okay? Now, this theta, remember, in this unit, this is going to be in radians. You learned a long time ago that the equation relating the angular distance rotated through, or angular displacement rotated through in a circle, to the linear distance traveled along the perimeter, the circumference, is s equals r theta. Theta has to be in radians. And again, I'm just going to make a little note. This is usually known as the angular, I'm spelling that wrong, angular displacement. Okay, you learned this a long time ago. It's really important though. It is the bridge between measuring things in meters, measuring linear distances and displacements, and measuring the angle that something rotates through. Because if something's rotating around some fixed point, then obviously there's a good chance it's also moving over a linear distance. We need a relationship between the angle it rotates through and how far it's actually traveled. And that depends on the size of the radius. We're going to move and talk about angular speed now, and my goal with the rest of this is to show you that a lot of the kinematics equations that we've already learned, they're going to come back up. We're just going to have them slightly rewritten to show that we're talking about angular displacements and angular speeds and velocities and angular accelerations. The equations are going to have the exact same format. We know that the linear speed of an object, linear speed or velocity, can be found by using this equation. V equals change in distance over change in time. You've known that since the very beginning of the course. Well, the angular speed, the equation looks almost exactly the same, but the variables are changed around. Let's think about it. If we're talking about a linear distance, we're talking about measuring something in meters, that's d. When we're talking about angular motion, we're not talking about a distance traveled anymore. We're talking about an angle rotated through. How much did something rotate? What's the angular displacement? Well, the angular displacement symbol is theta. So we're going to have, instead of d, we're going to have a theta. You just need to get used to, in this topic, using theta as the symbol for how much something has rotated. There's no such thing as angular time. Time is a scalar. Time is time. Okay, there's no angular time or anything like that. So you see that the equation is of the same form, and the variable name is also a little bit different. It looks like this kind of curly W thing. Okay, curly little W. Do not call it W because that is not correct. Its actual name, it is a lowercase omega, which is a Greek letter. That is the technical name for it. That is the name you should be calling it. For whatever reason, my classes never end up calling it omega. Please don't ever call it W. I will tell you that that's wrong. Call it omega if you can. For some reason, everyone always ends up calling this wumbo. That's just what it is. That's how it's worked for whatever reason. It's kind of funny, but the technical name for it is omega. But if you say wumbo, I'll know what you're talking about. No one outside this room will know what you're talking about, which is fine. Okay, but the technical name is omega. Now, we do need to talk about the relationship between the linear speed and the angular speed, and that's going to have to do with our relationship between linear distance and how much something has rotated, the angular displacement. So a relationship between V and omega. All right, so let's think about it like this. We have this equation, S equals R theta. Imagine with an equation, I can do the same thing to both sides and the equation will stay the same. I'm going to divide both sides by t. Now, S is not our normal unit, or our normal letter or variable for distance, but think about it as distance. This would be distance over time. Okay, it is a linear distance, distance over time. We know that that's velocity. That's v, or technically speed. Now, theta over t, theta is the angular displacement over time, Look, we just said what that was. That's omega. That's the angular speed. R, so if I'm dividing theta by t, I get omega times this r, which is still there, not getting divided by t, and I get this. The linear speed is related to the angular speed by this equation, v equals r times omega. In other words, if you want to find the linear speed and you have the angular speed, simply multiply by the radius. If you have the linear speed and want to find the angular speed, take the linear speed, divide by r, you have the angular speed. By the way, the units of angular speed are not meters per second. Since this is in radians, it is radians per second. I do want to make one more note about constant rotation, and it goes back to something that you learned back in the circular motion unit. For something that is rotating or moving in a circle, we know that the speed is v equals 2 pi times r over t. Now the rules of math say I can multiply both these sides by t, I can divide both these sides by v, and I will end up with this. T, and I'm going to make it uppercase T because this T stands for the period. 2 pi r is the circumference. T is the period. That's how much time it takes to go around the circumference once. So I'm going to do capital T equals 2 pi r over v. Perfectly valid equation, just a rearrangement of this. Now what if I want to relate the period to the angular speed? I know from this equation that v is equal to r omega. So I'm going to substitute 2 pi r over r omega. My r's cancel out, and I'm left with this. The period of something that is rotating in a circular motion is equal to 2 pi over the angular speed. Okay? 2 pi divided by the angular speed, how much of an angle it's rotating through per second. I think that's on the reference tables. That's why I'm showing it to you. It doesn't come up too often, but since it is on the reference tables, I did want to point that out to you. Let's move on and talk about angular acceleration. Very similarly to speed, the linear speed and the angular speed, there's another equation that relates these two, or there's math that relates the two of them. We know that linear speed, linear acceleration is given by this equation. A equals delta v over delta t. I bet you can guess what the angular equation counterpart would be. Angular acceleration simply means the rate at which the angular speed or the angular velocity is changing. Okay? Linear acceleration just means how much the linear velocity is changing. So angular acceleration means the same thing, but with angular variables. Okay? How much something is speeding up or slowing down its rotation per second. Linear variable for speed is v. The angular variable for angular speed is omega, so this becomes delta omega. Remember, t doesn't change, over delta t. And the variable this time, it actually kind of looks like an A, but it's not. It is the Greek letter alpha. Okay, this is a Greek alpha. Looks a little bit like the proportional symbol. I'm told it's not exactly the proportional symbol. This is a Greek letter alpha. Now, again, you should be calling it alpha. I have had people in the past refer to it as a goldfish or a Jesus fish. I know what you're talking about with those. No one else will. So please just try to refer to it as alpha. The issue with angular acceleration is there are actually two different types of acceleration when something is moving in a circle, because it could be speeding up or slowing down its rotation. But also, think about circular motion. There's always that centripetal acceleration. Okay? So angular acceleration, we got to talk about basically two different types of acceleration when things are moving, when things are rotating. The first one is what we're going to call tangential acceleration. And should be tangential angular acceleration. This is acceleration in the direction of motion. And what it does is it speeds up or slows down the rotation. Tangential, oh, never mind, it should not be angular. I'm sorry, I apologize. This angular acceleration refers to how the rate of rotation is speeding up or slowing down. We're going to relate it back to a linear quantity called tangential acceleration. In other words, how much an object is accelerating in terms of speeding up or slowing down in meters per second squared in the direction of its motion. Again, getting ahead of myself here, if we take v equals r omega, and we divide both sides by t. Velocity technically should be change in velocity, but divided by change in time is acceleration, and this is our tangential acceleration. So I'm going to do a sub t equals omega divided by t is angular acceleration. So the tangential acceleration of an object, in other words, the rate at which it is speeding up or slowing down linearly, is equal to the radius times the angular acceleration, the rate at which the rotation is speeding up or slowing down. However, we also have, so I'm going to box that in, we also have this other equation. We also have another type of acceleration, and that is centripetal acceleration. Remember, this is acceleration directed towards the center of the circle, towards the center of rotation. Directed toward center of rotation. You guys know that centripetal acceleration is AC equals v squared over r. Remember that v is r times omega, so I could rewrite this as r omega squared over r, which would end up being r squared times omega squared over r. One set of r's cancel, and I'm left with this. If you want to talk about the centripetal acceleration, in other words, the rate at which the angle, how do I want to say it? The rate at which the rate at which the direction is changing, and you want to use angular variables, it ends up being omega squared times r. Again, these don't come up too much, but I do want to show you where those equations come from. The last thing I want to do is I want to finish out showing how the linear equations have angular counterparts. You'll notice that linear speed equation looks very similar to angular speed equation. Linear acceleration equation looks very similar to angular acceleration equation. They just have different variables. Okay? They have the same basic meaning. It's just different variables to tell us whether we're talking about linear motion or angular motion. The angular kinematics equations are those three kinematics equations we've been using all year. They have the same format as the linear equations, but with angular variables. So they look like this. Remember your fiat equation from earlier in the year and from last year is VF squared equals, VF equals VI plus AT, or V equals V naught plus AT. We're going to have the same thing, but with angular variables. Instead of V, we're going to substitute in omega, and instead of A, we're going to have alpha. So that's omega equals omega naught plus alpha multiplied by time. Look at the format. It's very similar. Number 2. Remember your x equals x naught plus v naught t plus 1/2 at squared? Same thing, except where it's going to be this time theta equals theta naught. Remember, those are angular displacements, how much of an angle has been rotated through in radians, plus omega naught t plus 1/2 alpha t squared. And finally, the third one, which is v squared equals v naught squared plus 2a x minus x naught, is now, for angular variables, omega squared equals omega naught squared plus 2 times alpha times theta minus theta naught. I hear the same complaints about this every year, people saying, I don't get this, these equations are weird, I don't like them, they're uncomfortable. These are the exact same equations you have been using all year. Now they're just referring to angular variables, so they have different variables in them. Okay, you need to know that theta now is kind of like distance. It's how much of an angle has been rotated through. Omega is angular speed, and alpha is angular acceleration, all just dealing with angular motion. Instead of being concerned with how far something travels in meters, we're now concerned with how much something rotates. I'm going to stop there. We'll do some examples in the next video.